58 million years ago, in the sweltering jungle swamps of what is now Colombia, a predator moved through the black water. It was not a dinosaur. Those had vanished several million years prior. It was a serpent, but to call it a snake is to dramatically understate its physical reality. Today, the green anaconda holds the title of the world's heaviest snake, topping out around 550 pounds. The creature patrolling the Paleocene wetlands weighed more than a compact car. It was as long as a school bus. It could crush a prehistoric crocodile with the same casual effort a human uses to snap a twig. This is Titanoboa cerrejonensis. For 10 million years, it was the undisputed king of the neotropics. But the story of Titanoboa is not just about size. It is a story about heat, physics, and the absolute biological limits of life on Earth. To understand this apex predator, we must first understand the world that forged it. Following the KPEG extinction event that wiped out the non-avian dinosaurs, the global ecosystem was left in a vacuum. Evolution abhors a vacuum. In the geological epoch known as the Paleocene, the Earth was experiencing a greenhouse effect of intense magnitude. Atmospheric carbon dioxide levels were skyrocketing. Global temperatures surged. Nowhere was this more profound than in the neotropics of South America. This region was a hot, humid rainforest system, distinct from the Amazon we know today. It was wetter, denser, and significantly hotter, averaging about 90 degrees Fahrenheit. But here is the part that changed our fundamental understanding of reptilian biology. Reptiles are poikilothermic. They rely on ambient temperature to regulate their metabolism. In the modern world, snakes are limited in size because they cannot maintain the metabolic rate required to power a massive body if the air is too cool. A snake the size of Titanoboa would freeze to death in today's tropics. Therefore, Titanoboa is more than a fossil. It is a paleothermometer. Its very existence proves that the Paleocene tropics were much hotter than previously believed. The heat unlocked a biological door, allowing cold-blooded animals to grow to sizes previously reserved for the dinosaurs they replaced. The evidence for this giant was uncovered in one of the most unlikely places on Earth, the Cerrejon coal mine in La Guajira, Colombia. This is one of the world's largest open-pit mines, a vast terrace scar in the Earth that strips away millions of years of geological history layer by layer. In the early 2000s, researchers from the Smithsonian Tropical Research Institute and the University of Florida began noticing fossils amidst the coal. They found giant turtles with shells the size of kitchen tables and crocodiles with blunt, crushing snouts. Then they found the vertebrae. At first glance, a snake vertebra looks fairly standard, a complex socketed bone. But when paleontologists placed the Cerrejon fossil next to that of a modern anaconda, the scale was difficult to comprehend. The prehistoric vertebra was T-shaped and dwarfed the modern specimen. By extrapolating from the size of the vertebrae and comparing them to modern boas, scientists arrived at the numbers. Titanoboa stretched 42 to 45 feet in length. It weighed approximately 2,500 pounds. We have recovered fossils from 28 individuals. This wasn't a genetic anomaly or a singular monster. This was a thriving, dominant species. Anatomically, Titanoboa was a boidae, a member of the boa family. However, its mechanics were dictated entirely by gravity. On land, a 2,500-pound snake is a biological impossibility. The friction required to move that much mass would be immense, and the skeletal structure would likely collapse under its own weight without the buoyancy of water. This tells us that Titanoboa was almost exclusively aquatic. It lived a life similar to the modern anaconda, but on a macro scale. It navigated the river systems of the Paleocene, its body supported by the murky depths. Its ribs were robust, designed to withstand water pressure and the immense physical stress of constriction. But here is where the science takes a turn. While it was a constrictor, the skull fragments suggest a different hunting style than we might expect. Titanoboa had a massive gape, but its teeth were numerous and recurved, angled backward. This dentition is characteristic of piscivores, or fish eaters. In the Cerrejon Formation, fossils of giant lungfish and dinosaurs, ancient relatives of crocodiles, are abundant. This suggests Titanoboa wasn't just an ambush predator waiting for terrestrial prey to drink at the water's edge. It was an active hunter of the deep river channels. Consider a moment in the life of this animal. The sun beats down on the dark surface of a sprawling oxbow lake. The heat is oppressive, the air thick with humidity and insects. Beneath the surface, the water is brown and silt-heavy. Titanoboa rests on the riverbed. It does not need to move. Its metabolism, though high for a snake, allows it to remain motionless for hours, perhaps days. It detects pressure waves before it sees anything. A localized disturbance in the water. A 6-foot lungfish is navigating the gloom. Titanoboa does not strike immediately. It is immense, and energy conservation is paramount. It waits until the prey is within the strike radius, a zone of death less than 10 feet from its snout. When it moves, it is an explosion of hydrodynamics. The head launches forward, displacing water, the jaws unhinging to maximize the capture area. The backward curving teeth snag the slick scales of a lungfish. There is no venom. There is no need for it. The snake coils. This is not about suffocation, as commonly believed. Constriction halts the blood flow. It overwhelms the prey's cardiovascular system. The lungfish struggles, but against 2,500 pounds of muscle, the outcome is mathematical. The struggle ceases. The snake consumes the meal whole, a process that takes hours, leaving it vulnerable yet unassailable. For the next month, it will not need a hunt. It simply exists, a massive organic engine fueled by the heat of a greenhouse world. Before we look at why this titan fell, a quick word about the future of our own ecosystems. This journey into the Paleocene reminds us how fragile habitats are. If you want to play an active role in preserving the biodiversity we have left today, consider looking into Planet Wild. They are a community-driven organization dedicated to rewilding the planet. They don't just talk about conservation, they fund direct action, from clearing plastic in the oceans to protecting endangered species reserves. It's a way to turn a monthly subscription into tangible, boots-on-the-ground impact. It is efficient, transparent, and vital. Now, back to the decline of the giant. Titanoboa's dominance was absolute, but it was tied to a single, critical variable: temperature. The hyperthermal conditions of the Paleocene did not last forever. As the epoch transitioned into the Eocene and eventually moved toward the Oligocene, the Earth began a slow cooling process. The global thermostat dialed down. For a mammal, a drop in average temperature is manageable. We generate our own heat. For a cold-blooded organism weighing over a ton is a death sentence. As the tropics cooled, the metabolic math of Titanoboa stopped working. It could no longer hunt effectively, digest properly, or grow to such massive sizes. The advantage of size became a liability. Smaller snakes, requiring less ambient heat and less food, outcompeted the giant. Titanoboa vanished from the fossil record around 58 to 60 million years ago. The forests it inhabited changed, the water systems shifted, and the lineage of the giant constrictors shrank back down to the scales we recognize today. The discovery of Titanoboa forces a humbling perspective on human history. We often view the timeline of Earth as a build-up to the arrival of humanity. But Titanoboa thrived for millions of years, far longer than Homo sapiens have walked the planet. It was a master of a world we would find uninhabitable, a world of sweltering heat and deep water. In the coal mines of Colombia, we burn the remnants of that ancient forest to power our modern lives. We dig through the carbon that once constituted the ecosystem of the largest snake to ever live. It serves as a stark reminder that on a geological timescale, size and dominance are fleeting. The Earth changes, the temperature shifts, and even the giants are eventually reclaimed by the rock. Titanoboa was the apex of its time, a creature of perfect adaptation, until the moment the world moved on without it.